Right. Hi, welcome to question number 5 of the exam questions that we were having a look at within magnets and currents examples. And here they give us a wire, a complete circuit with no battery or EMF source whatsoever. And here there's an ammeter, and that's a coil. The ammeter is something used to measure amps, so that's current. And we're going to talk about things that happen in this circuit. And since there's no EMF source, we should be suspecting probably that we're going to get something to do with induction, magnetic induction. And to confirm our suspicions, here there's a magnet, and so by moving this magnet, its magnetic field lines, or magnetic field that it produces, those lines are going to be cut by this wire that's here. And therefore, whenever you have a wire in a complete circuit connected, cutting through magnetic field lines, you're going to have an induction effect, as Faraday discovered. And if you want to find out what direction things are induced and all of that, then you need to use Fleming's hand rule. But since here we're generating electricity, whenever you're generating, you use the right hand rule. Okay, that's how I remember it. Generate electricity is really important, and my right hand's the most useful one, so that's how I remember them. So the right hand for generation of electricity, generating an EMF or a current, generating a current. The EMF produces a current. And the left hand is useful when you want to find out what direction something moves, when it's inside of a magnetic field and there's a current there. Okay, so let's see what the question actually says. Question here says, state what you would expect. Well, actually, first let me read the preamble for the question. The diagram below shows a permanent magnet being moved towards a coil whose ends are connected to a sensitive ammeter. Says sensitive because these currents are normally very small, so that would be a galvanometer normally, and galvanometer and an ammeter is the same, but galvanometer is more sensitive. It says, as the magnet approaches, the ammeter needle gives a small deflection to the left. So the needle there, if this is the reading of the needle, then if this is the pivot of the needle, it moves to the left by a little bit when this moves in that direction, right? So this is the ammeter, and that's what they observe. Now in part A it says, state what you would expect the ammeter to show if in turn, so instead of this happening, then the magnet was pulled away from the coil. So this, if you're not very sure about any of this, you should go back to the video on, probably the second video on induction will tell you about this, but watch the first one also if you haven't seen it yet, because otherwise all of this would be a bit meaningless. So if the magnet is pulled away from the coil instead of towards, what happens is that the magnetic field lines cut by this coil are gonna, let me draw them for a second. So this is really, that happens, and then like that, and then like that. Yeah, they don't cross. I drew them wrong, but they will be like that, and they cross these lines. So as you move them, this crossing magnetic field lines through the wire, that's what really is causing the EMF induction. So if we move them in the opposite direction, these are being crossed, but they're crossed in the opposite direction. So actually what's going to happen in part A is that the ammeter is going to move, but in the opposite direction. So moves in the opposite direction, which means opposite direction. That basically means that the EMF being induced in this circuit is instead of in one direction, it's in the other. So that means that the current induced moves in the opposite direction. Okay, so hopefully that makes sense. Now, part B it's part A contains several parts. So that was part 1 within A. Now part 2 says the magnet was reversed so that the south pole was moved towards the coil. So you turn it around and then you move the south pole towards the coil there. That will have the same effect as this thing on the top. It would still move to the right. I should be using yellow for be consistent. It would still move to the right, so the same as above, same as in part 1. So EMF is reversed. If instead of the North Pole it is the South Pole that moves closer. Hopefully that's a little bit intuitive for you. In part 3 it says the direction of the current, part 3 says the magnet was now pulled away from the coil at a much higher speed. Okay, so it's pulled away, so here is being pulled towards and it moved to the left. So here it's going to move away, so it's going to move to the right instead of the left. It's going to move to the right, but it's a much faster speed, so really the induced EMF has to do with the rate of cutting of the line. So if it's much faster, then the EMF will be larger. Is larger and opposite direction to the original in which it was moving to the left. Okay, so if here it moved to the left and the current was going in one certain direction, then now if you move it away it's going to move in the opposite, and since you're moving it faster, the current itself is going to be bigger. So hopefully all of that makes sense. And then the very last one is really easy. It just says give the name of the process which is illustrated by this experiment. And that's just, if you know this you feel very good, and if you don't know it's a bit of a bummer, but if you do know it you just say electromagnetic. This process is called electromagnetic induction, and the law was discovered by Faraday, even though the hand is called the Fleming's right and Fleming's right left hand rule. Electromagnetic induction is the process called, or the phenomenon. So the next question, question 6a, said the chemical energy stored in a fossil fuel produces heat energy when the fuel is burnt. Describe how this heat energy is then used to produce electrical energy at the power station. And it's only 2 marks, so it's not that much, but we're going to go into a little bit of detail with it so that you know how to answer it, even if it was for more marks. And this has a lot to do with the ideas that we've been looking at on the previous questions, basically with generators. Okay, so in a chemical power station like with coal, what happens is, summary would be that they bring in all the coal, which is like this in a mountain, and they use conveyor belts to send the coal all the way up into a pulverizer. So it falls in here, and then in the pulverizer it comes out really, really thin, and then it gets fed into this huge tank which has these pipes like that with a lot of surface area of water, and here the coal is burnt with this is always kept at a huge temperature, and the coal is being fed, and this is like a furnace with fire here, and all of this is really hot, and the water that comes into here gets converted into steam. So the water that gets converted into steam then is moved at really high speeds and high pressure through turbines, and the turbines have kind of moving parts that have electromagnets on them, and they rotate along with the parts that are being shoveled around really, really quick by the water that goes through. And as the electromagnets move around, they produce electricity in the fixed coil. So here, instead of the coils moving around, the electromagnets move around and the coils are fixed, and then coils therefore cut the magnetic fields from the electromagnets, which are whizzing around really fast, and so that produces a huge EMF, and then the electricity is then passed into transformers where the voltage is stepped up, really, really high voltage, and then these are fed into the grid. And the water is then cycled around again, and it goes into a lake where it cools down. This heat reservoir here cools it down, and it's picked up from here again. to go back there. So that's a closed cycle with the water and a closed cycle with the electricity, really, although most of the power is used along the way. So this is more or less how the general scheme of the power plant works. We'll talk about why the voltage is so high in a bit, because they actually ask about that, but it's important to know more or less how this goes. And the actual way that the electricity is converted, if you want to think about the more simple idea, then you should look at a detailed diagram of a generator. And a generator, you would normally see it as normally they paint very often the magnet as a static thing, and the coil here as the rotating thing. So they have a shift. They have a shaft here in the middle, and they have a coil around it, and the coil is what's rotating around, and the coil is attached to some rings here. One of them is attached to there, and this one continues and attached to another ring over here. And as these two rotate, they come in contact with brushes, which are located here on the side, in contact with the rings. That's a really bad diagram, sorry, but hopefully you get the idea. And the brushes then are part of a circuit, like so, which are powering some load. It can be a light bulb or whatever. And so what is happening here is that these are fixed magnetic field lines from north to south, and as this wire coil, this is rotated by some by something here. In this case we were talking about steam, so this makes this rotate, and then the coil here would rotate around, cutting the field lines. That would generate an EMF current around this circuit, and that would be transferred to the two rotating slip rings, and the slip rings would transfer all those electrons to this circuit, and then you would power this here. In the example that we had here, actually it was electromagnets that were spinning around in a fixed coil, but it's the same principle. What's important is that you have relative movement between them, and that the field lines themselves are being cut, so it doesn't really matter the order in which that's happening. Now you can do this cleverly to produce AC current, which is really what these use, and AC current is used normally because you have a larger transfer of current, is more efficient. And there was a big fight between Tesla and Edison about this a long time ago, and Tesla ended up winning in the end, even though Edison tried to prove that the AC was dangerous and was killing animals and electrocuting them to convince people. It was pretty dramatic. I recommend you watch documentaries about Tesla. He was a pretty fascinating guy, and I think much more inspired than Edison. Anyway, we'll talk more about alternating current and alternators. And so this is quite a lot more involved than what you would be expected to write down for 2 marks, but if you just had to write down for 2 marks, then I would write this diagram here with the two rings, and the coil here, and the permanent magnet here, and the coil is going around, and what makes that go around is this turbine, and this turbine would be turned around by steam at high pressure and velocity. Okay, and that steam is heated up by the coal that is burnt, and that's would be enough for the marks, or you could just explain it all in words, and that would be fine too for 2 marks. Okay, so just to move on, because we don't have very long, see if we can finish this in this video. Part B basically asks why do we use high voltage? Why high voltage? High voltage to transport electricity, to transmit electricity. And the answer is basically that they've found out that with high voltage the energy loss is smaller, so there's less power loss at the high voltage. So by using a transformer to stepping up the voltage, they can use lighter cheaper cables, basically cheaper cables